Okay, now let's solve some DEs using Laplace transforms. Like this one here, that's second order, non-homogeneous, linear. It's an IVP. We know how to solve this. You probably solve something like this in test 2. Like, we know how to do this. So this is just an alternate method of doing it. We're going to be doing much less calculus. In fact, we're not doing any calculus at all. We're going to take Laplace transforms and then do algebra. That's the whole point of the Laplace transform, is it makes the calculus part easier, but there's a trade-off. You have to do a bunch of algebra now. So let's do it. We're going to take the Laplace transform of both sides. Okay. Now we got to remember the Laplace transform of y of t, we just call capital Y. Lowercase y with the t's, capital Y with the s's, and you got to keep those separate. You're going to confuse yourself if you don't. You got to really draw it so that you can easily tell if you've got a capital or a lowercase. The Laplace transform of the derivative. So this is one of our formulas we have in here. They're using capital F instead of capital Y and lowercase f, and you see that. It's going to be S times capital Y minus y of 0. Little y of 0 here, one of our initial conditions. We don't have a y prime in this one, but I did want to write that down. The Laplace transform of the second derivative, it's going to follow this same pattern. Instead of having an s here, we're going to have an s squared. The order of the derivative tells you what power goes there. And now the s's are going to go down while these conditions go up. Minus s y of 0 minus, no more s anymore, y prime of 0. If this were fourth derivative, I would have an s to the fourth here, and the s's would keep going down in power while my initial conditions would be going up in order. I would have y of 0, then a y prime of 0, then a y double prime of 0, and so forth. So the s's go down while the y's go up in order. And we have to know these initial conditions. If we don't know those, we can't use Laplace transforms. Laplace transforms only solve initial value problems. Okay, so let's plug all that in to our DE, the left side. I'm going to get s squared capital Y minus s y of 0. I'm going to write all this out in all its glory for now. Minus that right there. Here, let's write that out. Is the Laplace transform of y double prime. Minus Laplace transform of y. So I distributed here. The Laplace transform is a linear operator. I can distribute. Laplace transform of little y is just capital Y. Equals Laplace transform of sine. So I got to go to my table and look that up. I don't remember it. We just have sine of 1t here. So it's going to be 1 over s squared plus 1. Remember, at this point, you shouldn't have any t's anymore. Once you take the Laplace transform, you're over in S domain. So this here is the Laplace transform. These are L's that I'm drawing. I know my L's look really crappy. That's the Laplace transform of sine of x. So no x's anymore. Okay, y of 0 was 0. Y prime of 0 is 1. So that gives me an s squared capital Y minus 0 minus 1 minus capital Y equals 1 over s squared plus 1. So combining everything together, I get an s squared capital Y minus a capital Y minus a 1. From here, I can factor out a capital Y. Let's move that 1 over first. Let me write it like this. And if I factor out this capital Y, I get here s squared minus 1. So look at my original DE. That's second order minus 1 times 0th order. Here I get an s squared. That looks a lot like when we were doing homogeneous DEs and we get our characteristic polynomial. It is. That's going to happen every time. The function of s you get here, it's literally always going to be your characteristic polynomial times y. Always. What's going to change in problem to problem is whatever is left over here that doesn't have y's in it. You might have extra s's left over here. If y of 0 weren't 0, I would have had an extra s left over. And then I pick up a number from this. I want to make sure that looks like a y right there. That's a y. So it's these guys right here that are going to make this different from just having your characteristic polynomial hanging out. Those are the ones you really got to be careful with. And you got to be really careful with distributing negatives. If we've got negatives, or if I had a 3y in there and distributing the 3, you got to be careful. Okay, from this point on, it's just an algebra problem. Y now we'll be dividing that over 1 over s squared minus 1 plus s squared plus 1 times s squared minus 1. Now it just comes down to partial fraction decomposition. So you've got a bunch of different ways you can do this. You can do partial fraction decomp on each term one at a time. If you want, I can deal with this guy first. The Laplace transform is a linear operator. So I can do it piece by piece. And that's the way I prefer to do it. I would do this piece first, find his inverse Laplace transform, then completely separately do this one. But just for, I guess most students don't like to do it that way. They like to squish it all together. So I'm going to do this one all together. I'm going to do like a full partial fraction decomposition. So that factors 1 over s minus 1 s plus 1 plus I was factoring this 1 s plus 1. And here's why I wouldn't want to have to do all this at once. In order to do just one single partial fraction decomp, I got to combine these fractions together. I got to get a common denominator and combine them together. I mean, it's not hard. I would have to multiply this one here, top and bottom, by s squared plus 1. I'm just going to do this, plus that one. Now I have a common denominator. I can add it all together. So I get this. Plus 2, sorry. S squared plus 1 more. Okay, now I can do my partial fractions. And I'm just doing it all in one big go. Okay, so I want to think of this as order doesn't matter here. I'm going to do it in the order I think makes most sense. A over the s minus 1, B over the s plus 1. And then here, this is an irreducible quadratic. I have to do a linear factor on top, CS plus D over S squared plus 1. And now it's just a matter of doing the partial fractions. So I like the clear your denominators method, multiply everything by the LCD. And that'll give us S squared plus 2 equals, each one of these fractions is going to pick up everybody they're missing. He gets an S minus 1 and an S squared plus 1. And then this guy here on top will get the S minus 1 and the S plus 1. So all that stuff you learned with partial fraction decomposition back in pre-calc, and then you used in Calc 2. Yeah, we're going to be using it all now. Now from here, personally, I like to just solve these by hand. I use the cover-up method by plugging in strategic values of S to make certain things cancel out. You can also just multiply all this out and match up coefficients. Like, for example, I can see here, if I were to multiply this out, I would get an A times an S cubed plus a bunch of other stuff. If I multiply this out, I would get a B times an S cubed plus a bunch of other stuff, but no other cubes. And then here, I can't do this one in my head. This was S squared minus 1. I don't think I'm going to get any cubes here. It's impossible to multiply any of this out and get a cube. Oh no, right there. It's right in front of me. CS times S squared, there's going to be a C S cubed. There's no S cubed on the left-hand side. So these must all add up to 0 S cubed. So we could do that. We have 4 unknowns, we get 4 equations and get this big long system of equations. A perfectly legitimate way to do it. Seems to take forever. So I like the cover-up method. I would go through here and plug in S equals 1 because I know that makes this thing 0 and it makes this thing 0 right there. So if I plug in an S equals 1 everywhere, I get 1 squared plus 1, 3 from right here, equals A times 1 plus 1, 2. Another 1 plus 1, 2. This is 0, and this is 0. Hey, I just solved for A. A is 3/4. Plug in S equals -1, and I can solve for B. Because this will be 0, and this will be 0. So -1 everywhere. Looks like I'm still going to get a 3 there. -1 squared plus 2 equals 0 plus B times -1 minus 1. That's a -2 times a 2. And then all that is 0 again. So I think B here equals -3/4. Now that I got A and B, I could find C. Using this first equation I wrote out here. Are we getting C equals 0? I think we are. So I could go, my point I'm making here is I could go through and do all this by hand, and that's absolutely worth doing. Absolutely. But there are a lot of places you can mess up. So my goal with the test is not to judge your ability in a time stressful environment to be able to do partial fractions. Like I think right now I'm getting C equals 0. It's possible I've done goofed in here somewhere. On a test, you don't have to go through all this. I want to see you get to here. Get to here, maybe even this line. Like I like this line here. And then let's just use Wolfram Alpha to do the PDF or PFD. Let's just type this in to Wolfram Alpha. It'll do that for me. I don't even have to tell it that's what I want to do. It'll just do it. We got S squared plus 2 divided by, I got to be careful here, extra parentheses. Let's say we had an S squared plus 1, an S minus 1, and an S plus 1, double parentheses on the bottom. Yeah, C was 0. Look, I had A and B right. There's my 3/4, my negative 3/4. C was 0 because there's nothing, there's no S on top. And D was negative 1/2. So I was almost there. Okay, so we've got our partial fraction decomposition. So I'm just going to dot this. We've got then capital Y equals, we had a 3/4, a negative 3/4, and a negative 1/2. And what were these over? I don't remember which was which. The positive was over S minus 1. This was over S plus 1, and this was over S squared plus 1. Okay, now we just do the inverse Laplace transform. So then just take the inverse, I think I even have room in here. Do the inverse Laplace transform of each of these. These are going to be exponentials. That's going to be a sine or a cosine. Then little y of t is the inverse Laplace transform. Oh, my pen's not writing for some reason. Inverse Laplace transform of capital Y. That is going to be 3/4 e to the t. That's e to the negative t. This is going to be, let's see, I think that is a sine of kt. K equals 1. Yep, that's just a sine of t. So the 1/2, the negative 1/2 just comes along for the ride. We get sine of 1t. And we have solved the differential equation without doing any calculus at all. Okay, and then for completeness, let's do this problem. This one's going to be much harder, I'm afraid. Take the Laplace transform of both sides. Okay, Laplace transform of y double prime is going to be S squared capital Y minus S y of 0 minus y prime of 0. This 2 is going to come along for the ride. We've got to be careful with that too. So plus twice Laplace transform of y prime is S capital Y minus y of 0 plus 5. Laplace transform of little y is capital Y. The Laplace transform of e to the negative 2t will be 3, the 3 comes along for the ride, and then we get an S1 over S plus 2. Okay, we fill in our initial conditions. So S squared capital Y minus, let's see, Y of 0 is 1, so minus S. Y prime of 0 is 1. Got to distribute this 2 here. I'm going to have a 2SY minus 2. You got to be careful right there. Y of 0 is 1, but that 2 plus 5 capital Y from right here. Grab everything together with a Y. So I'm going to have a capital Y, S squared plus 2S plus 5. Go back up and look. 1, 2, 5. 1, 2, 5. That will always happen every time. Everybody that has a capital Y in it, you factor it out, you're going to get literally the same thing as your characteristic polynomial. It's all the extra stuff that matters. I've got this negative S. So here, I've used up these guys. I've got now minus S minus 3. Okay, move those to the other side first. That's an S, not a 5. Unfortunately, my 5s and S's sometimes look too much alike. That's a 5, that's an S. Move those guys to the other side first. So 3 plus S plus 3 over S plus 2. Then divide by this thing. So I'm going to have 3 plus S over S squared plus 2S plus 5 plus my S's and 5s look a little too much alike here. Okay, now it's just partial fraction decomposition. And there's going to be a whole lot of it. We can combine these together into one single fraction and then just do it once, or we could just work with each one separately. On this one, I'd probably go ahead and combine them together. Since we're going to have this irreducible quadratic on both of them, we're going to have to play that game at some point where we complete the square in the bottom. We got to play that whole game. So I think we don't want to do that over and over again. Let's combine these into one single fraction. So this fraction needs an S plus 2 top and bottom. Maybe I'll write that as S plus 3 times S plus 2 plus 3 more from here all over S plus 2, S squared plus 2S plus 5. Okay, so I want to write that. I guess we can go ahead and clean that up on top there. We're going to get, what do we got? We got an S squared. We're going to get a 5S, 2S plus 3S, so a 5S. Yay, we got another 5 in the problem. Plus 6, plus 3 more, so plus 9. And I want to write this. The partial fraction decomposition would be A over this linear factor. And then this is an irreducible quadratic. So that'll be BS plus C over this irreducible quadratic. And here, let's skip it. Let's just go ahead and type that into Wolfram alpha instead of going through all of that. Well, we got S squared plus 5S plus 9. divided by, and I need double parentheses here. I had the s squared plus 2s plus 5. Yeah. And then what was it? S plus 2. I'm missing a parenthesis there. See, look, you got to check. You got to check and make sure you typed it in right. A lot of mistakes can happen there. Still missing a parenthesis. Now we got it. See, it showed me there in green. There we go. Now it's in the bottom. The s plus 2 was showing up on top. And partial fraction decomp right there. So we get a 2s plus 15. And I think there was a 5 in the bottom. 5 times that irreducible quadratic. Of course, more 5s in the problem. I should try to avoid problems at 5s. My 5s and s's look too much alike. Plus 3/5 over the s plus 2. Of course, another 5. Okay, now we're doing inverse Laplace transforms. This one's going to be easy. That's just an exponential. Like this one, I know that's going to be 3/5 e to the negative 2t. This one's going to be hard. We're going to have to do a lot of work here. First thing I would do is complete the square. Let's write this one. Let's complete the square in the bottom. So I've got 2s plus 15. Is that right? Yeah. Plus 15 over 5 s squared plus 2s. And again, an easy way to think of this is I need a plus 1 here. So I'm going to break 1 off that 5 and have a plus 4. So that would be 2s plus 15 over 5. And that would be s plus 1 squared plus 4. I'm going to write that as 2 squared. Now here I'm going to get sines and cosines times exponentials. So I don't like having this 2 there. In the formula for cosine, there's no 2 in front there. So I got to factor out that 2. There's going to be a whole lot of weird math that happens here. So I got to pull this 2 out. I'm going to pull out that whole 2/5. That'll give me s plus 15 over 2 over this. I'm supposed to have an s plus 1 here. That's what's in the formula. I've got some extra stuff there. I got to add and subtract in a 1. And then split the fraction up. This piece here is going to be a cosine, and it already fits the form perfectly. That's exactly how it's supposed to look. This piece here is going to give me a sine, but I may have to do a little more adjusting to it. And don't forget about this 2/5 out front. Okay, so this guy here, I'm happy. Got to play with this one. So I'm just going to work with this one here. Let's see, that's negative 2 over 2. That's 13 over 2 times 1 over s plus 1 squared plus 2 squared. The sine formula is supposed to have whatever's being squared here needs to be up on top. So I need a 2 up on top. So I need to put in a 2 here and bring out a 2. If I'm putting it in, I need to bring it out. Now it looks right. Okay, so this will be a 2/5 times this first guy, s plus 1, s plus 1 squared plus 2 squared. I'm going to distribute this 2/5 here, plus a 2/5 times a 13/4 times a 2 over s plus 1 squared plus 2 squared. Okay, I know the inverse Laplace transform, so take the inverse Laplace transform of everything. Say take. So I get a 2/5. This is a cosine. That's going to be e to the negative t cosine of 2t. I think that's 26 over 20, or yeah, I guess we could reduce that. Let's see, what are we going to get? 13 over 10. That's a sine, or the exponential times a sine. And then we can't forget about that other guy we did earlier, this guy here, 3/5 e to the negative 2t. Now, what are the chances I didn't make any mistakes in there at all? Let's check and see. This is why I wrote down the answer. 3/5 to 13, that's exactly right, which surprises me. So you can see here, there are a lot of places you can make a silly mistake, but it really is all algebra. So on a test, I want you to go through all this. I want you to get down to here. You can absolutely, if you want to do the partial fraction decomposition by hand, that's fine. Honestly, I probably would too, just because it's kind of fun. But I would absolutely, definitely check your Laplace transform, or check your partial fraction decomposition using Wolfram alpha. Absolutely check it. And if you did do it by hand and you made a mistake, fix that mistake. Like, remember, I grade everything you turn in. So if you turn in something that's incorrect and you just kind of pretend it didn't happen, I have to take points off. Or just erase that part and just go, I used Wolfram alpha. Here's the partial fraction decomposition. Then you got to hammer everything into the correct form so it looks like something in the table and do the inverse transform. Okay, that's a good place to stop.